This is dark, and it has huge mass, and it's small. That's 3 smoking guns right there.
Right.
Implicating a supermassive black hole.
Nothing in this universe is scarier than a black hole. If you fell into a black hole left over when a star died, you would be shredded. Also, the massive black holes seen at the center of all galaxies have insatiable appetites. Furthermore, black holes are placed where the laws of physics are obliterated. Despite its horrors, black holes still have fascinated experts and the public alike for decades. However, after countless research efforts, scientists have yet to find any clues about what's inside a black hole. Fortunately, God doesn't let people down. Recently, scientists just captured the clearest image of one to date.
We physicists have waited 100 years since 1916 for this photograph. This photograph is the smoking gun.
While things have just gotten crazier, Michio Kaku and deGrasse Tyson just declared that we finally got a peek at what is happening inside of black holes, and the unprecedented discovery will provide new insights into the nature of these mysterious cosmic objects.
That's right, this is the most exotic, bizarre, monstrous object in the universe. You fall through that event horizon and you never come out. It's like a cosmic roach motel. Everything checks in, nothing checks out. In fact, our solar system could be devoured for lunch by this black hole, and the black hole wouldn't even burp. That's how big this monster really is, and we finally captured it on film.
Join us as we dig deep into black holes as well as what's inside these gluttonous beasts. Before we delve into the details of Michio Kaku and deGrasse Tyson's finds, this is everything you need to know about black holes. Black holes, simply put, are some of the strangest and most fascinating objects in space. They're extremely dense, with such strong gravitational attraction that not even light can escape their grasp. Albert Einstein first predicted the existence of black holes in 1916, with his general theory of relativity. The term black hole was coined many years later in 1967 by American astronomer John Wheeler, after decades of black holes being known only as theoretical objects. The first black hole ever discovered was Cygnus X1, located within the Milky Way in the constellation of Cygnus, the Swan. Astronomers saw that the first signs of the black hole in 1964 when a sounding rocket detected celestial sources of X-rays according to NASA. In 1971, astronomers determined that the X-rays were coming from a bright blue star orbiting a strange dark object. It was suggested that the detected X-rays were a result of stellar material being stripped away from the bright star and gobbled up by the dark object, an all-consuming black hole. Black holes are expected to form via 2 distinct channels. According to the first pathway, they are stellar corpses, so they form when massive stars die. Stars whose birth masses are above roughly 8 to 10 times mass of our sun, when they exhaust all their fuel, their hydrogen, they explode and die, leaving behind a very compact dense object, a black hole. The resulting black hole that is left behind is referred to as a stellar mass black hole, and its mass is of the order of the few times the mass of the sun. Not all stars leave behind black holes. Stars with lower birth masses leave behind a neutron star or a white dwarf. Another way that black holes form is from the direct collapse of gases, a process that is expected to result in more massive black holes with a mass ranging from 1,000 times the mass of the sun up to even 100 times the mass of the sun. This channel circumvents the formation of the traditional star and is believed to operate in the early universe and produce more massive black hole seeds. Such terror proliferating raises a question. After all, how many black holes are there in our universe? According to the Space Telescope Science Institute, STSI, approximately 1 of every 1,000 stars is massive enough to become a black hole. Since the Milky Way contains over 1 billion stars, our home galaxy must harbor some 100 million black holes. Though detecting black holes is a difficult task, and estimates from NASA suggest that there could be as many as 10 million to a billion stellar black holes in the Milky Way. The closest black hole to Earth is dubbed the Unicorn and is situated approximately 1,500 light-years away. The nickname has a double meaning. Not only does the black hole candidate reside in the constellation Monoceros, the Unicorn, its incredibly low mass, about 3 times that of the Sun, makes it nearly one of a kind. In 2019, the Event Horizon Telescope EHT collaboration released the first image ever recorded of a black hole. The EHT saw the black hole in the center of galaxy M87 while the telescope was examining the event horizon, or the area past which nothing can escape from a black hole. The image maps the sudden loss of photons, particles of light. It also opens up a whole new area of research in black holes, now that astronomers know what a black hole looks like. In 2021, astronomers revealed a new view of the giant black hole at the center of M87, showing what the colossal structure looks like in polarized light. Polarized light waves have a different orientation and brightness compared to unpolarized light. The new images show that black holes in even more detail. Polarization is a signature magnetic field, and the image makes it clear that in May 2022, scientists revealed the historic first image of the supermassive black hole at the center of our galaxy, Sagittarius A. Based on obtained data, we now know that black holes have 3 layers: the outer and inner event horizon and the singularity. The event horizon of a black hole is the boundary around the mouth of the black hole, past which light cannot escape. Once a particle crosses the event horizon, it cannot leave. Gravity is constant across the event horizon. The inner region of a black hole where the object's mass lies is known as its singularity, the single point in space-time where the mass of the black hole is concentrated. Scientists can't see black holes the way they can see stars and other objects in space. Indeed, astronomers must rely on detecting the radiation black holes emit as dust and gas are drawn into the dense creatures. But supermassive black holes, lying in the center of a galaxy, may become shrouded by the thick dust and gas around them, which can block the telltale emissions. Sometimes, as matter is drawn toward a black hole, it ricochets off the event horizon and is hurled outward, rather than being tugged into the maw. Bright jets of material traveling at near relativistic speeds are created. Although the black hole remains unseen, these powerful jets can be viewed from great distances. The EHT's image of a black hole in M87, released in 2019, was an extraordinary effort, requiring 2 years of research even after the images were taken. That's because the collaboration of telescopes, which stretches across many observatories worldwide, produces an astounding amount of data that is too large to transfer via the internet. With time, researchers expect to image other black holes and build up a repository of what the objects look like. Those discoveries will give us unprecedented insight into what the environment around a black hole looks like. So far, astronomers have identified 3 types of black holes: stellar black holes, supermassive black holes, and intermediate black holes. Stellar black holes, small but deadly. When a star burns through the last of its fuel, the object may collapse or fall into itself. For smaller stars, those up with about 3 times the sun's masses, the new core will become a neutron star or a white dwarf. But when a larger star collapses, it continues to compress and creates a stellar black hole. Black holes formed by the collapse of individual stars are relatively small but incredibly dense. One of these objects pack more than 3 times the mass of the sun into the diameter of a city. This leads to a crazy amount of gravitational force pulling on objects around the object. Stellar black holes then consume the dust and gas from their surrounding galaxies, which keeps them growing in size. Supermassive black holes, the birth of giants. Small black holes populate the universe, but their cousins, supermassive black holes, dominate. These enormous black holes are millions or even billions of times as massive as the sun, but are about the same size in diameter. Such black holes are thought to lie at the center of pretty much every galaxy, including the Milky Way. Scientists aren't certain how such large black holes spawn. Once these giants have formed, they gather mass from the dust and gas around them, material that is plentiful in the center of galaxies, allowing them to grow even more enormous sizes. Supermassive black holes may be the result of hundreds or thousands of tiny black holes that merge. Large gas clouds could also be responsible, collapsing together and rapidly accreting mass. A third option is the collapse of a stellar cluster, a group of stars all falling together. Fourth, a supermassive black holes could arise from large clusters of dark matter. This is a substance that we can observe through its gravitational effect on other objects. However, we don't know what dark matter is composed of because it does not emit light and cannot be directly observed. Intermediate black holes. Scientists once thought that black holes came in only small and large sizes, but research has revealed the possibility that mid-size or intermediate black holes, IMBHs, could exist. Such bodies could form when stars in a cluster collide in a chain reaction. Several of these IMBHs forming in the same region could then eventually fall together in the center of a galaxy and create a supermassive black hole. In 2014, astronomers found what appeared to be an intermediate mass black hole in the arm of a spiral galaxy. And in 2021, astronomers took advantage of an ancient gamma-ray burst to detect one. Astronomers have been looking very hard for these medium-sized black holes. Study co-author Tim Roberts of the University of Durham in the United Kingdom said in a statement, "There have been hints that they exist, but IMBHs have been acting like a long-lost relative that isn't interested in being found." Research from 2018 suggested that these IMBHs may exist in the heart of dwarf galaxies or very small galaxies. Observations of 10 such galaxies, 5 of which were previously unknown to science before this latest survey, revealed X-ray activity, common in black holes, suggesting the presence of black holes from 36,000 to 316,000 solar masses. The information came from the Sloan Digital Sky Survey, which examines about 1 million galaxies and can detect the kind of light observed often coming from black holes that are picking up nearby debris. Despite the theories accepted by most scientists, there is an ongoing controversy surrounding black holes. According to Michio Kaku, the best description of a spinning black hole was given in 1963 by the New Zealand mathematician Roy Kerr, using Einstein's equations of gravity. But there is a quirky feature to his solution. It predicts that if one fell into a black hole, one might be sucked down a tunnel, called the Einstein-Rosen Bridge, and shot out a white hole in a parallel universe. Kerr showed that a spinning black hole would collapse not to a point, but to a ring of fire. Because the ring was spinning rapidly, centrifugal forces would keep it from collapsing. Remarkably, a space probe fired directly through the ring would not be crushed into oblivion, but might actually emerge unscathed on the other side of the Einstein-Rosen Bridge in a parallel universe. This wormhole may connect two parallel universes, or even distant parts of the same universe. The simple way to visualize a Kerr wormhole is to think of Alice's looking glass. Anyone walking through the looking glass would be transported instantly into Wonderland, a world where animals talked in riddles and common sense wasn't so common. The rim of the looking glass corresponds to the Kerr ring. Anyone walking through the Kerr ring might be transported to the other side of the universe or even the past. Like the two Siamese twins joined at the hip, we now have two universes joined via the looking glass. Some physicists have wondered whether black holes or wormholes might someday be used as shortcuts to another sector of our universe, or even as time machines in the distant past, making possible the swashbuckling exploits in Star Wars. However, we caution that there are skeptics. The critics concede that hundreds of wormhole solutions might not have been found to Einstein's equations, and hence, they cannot be lightly dismissed as the ravings of crackpots. But they point out the wormholes may be unstable, or that intense radiation and subatomic forces surrounding the entrance of the wormhole would kill anyone who dared to enter. Spirited debates have erupted between physicists concerning these wormholes. Unfortunately, this controversy cannot be resolved, because Einstein's equations break down at the center of black holes or wormholes, where radiation and subatomic forces might be ferocious enough to collapse the entrance. The problem is Einstein's theory only works for gravity, not the quantum forces which govern radiation and subatomic particles. What is needed is a theory which embraces both the quantum theory of radiation and gravity simultaneously. In a word, to solve the problem of quantum black holes, we need a theory of everything. One of the crowning achievements of 20th century science is that all the laws of physics, at a fundamental level, can be summarized by just two formalisms. 1. Einstein's theory of gravity, which gives us a cosmic description of the very large, example galaxies, black holes, and the Big Bang. And 2. The quantum theory, which gives us a microscopic description of the very small, example, the microcosm of subatomic particles and radiation. But the supreme irony, and surely one of nature's cosmic jokes, is that they look bewilderingly different. Even the world's greatest physicists, including Einstein and Heisenberg, have failed to unify these into one. The two theories use different mathematics and different physical principles to describe the universe in their respective domains, the cosmic and the microscopic. Fortunately, we now have a candidate for this theory. It's called superstring theory, and almost effortlessly unites gravity with a theory of radiation, which is required to solve the problem of quantum wormholes. The superstring theory can explain the mysterious quantum laws of subatomic physics by postulating that subatomic particles are really just resonances or vibrations of a tiny string. The vibrations of a violin string correspond to musical notes. Likewise, the vibrations of a superstring correspond to the particles found in nature. The universe is then a symphony of vibrating strings. An added bonus is that as a string moves in time, it warps the fabric of space around it, producing black holes, wormholes, and other exotic solutions of Einstein's equations. Thus, in one stroke, the superstring theory unites both the theory of Einstein and quantum physics in one coherent, compelling picture. However, the curious feature of superstrings is that they can only vibrate in 10 dimensions. This is, in fact, one of the reasons why I can unify the known forces of the universe in 10 dimensions. There is more room to accommodate both Einstein's theory of gravity as well as subatomic physics. In some sense, previous attempts at unifying the forces of nature failed because a standard 4-dimensional theory is too small to jam all the forces into one mathematical framework. To visualize higher dimensions, consider a Japanese tea garden where carp spends the entire life swimming on the bottom of a shallow pond. The carp are only vaguely aware of a world beyond the surface. To a carp scientist, the universe only consists of 2 dimensions, length and width. There is no such thing as height. In fact, they are incapable of imagining a 3rd dimension beyond the pond. The word up has no meaning for them. Imagine their distress if we were to suddenly lift them out of their 2-dimensional universe into hyperspace, example, our world. However, if it rains, then the surface of their pond becomes rippled. Although the 3rd dimension is beyond their comprehension, they can clearly see waves traveling on the pond's surface. Likewise, although we Earthlings cannot see these higher dimensions, we can see their ripples when they vibrate. According to this theory, light is nothing but vibrations rippling across the 5th dimension. By adding higher dimensions, we can easily accommodate more and more forces, including the nuclear forces. In a nutshell, the more dimensions we have, the more forces we can accommodate. One persistent criticism of this theory, however, is that we do not see these higher dimensions in the laboratory. At present, every event in the universe, from the tiniest subatomic decay at exploding galaxies, can be described by 4 numbers: length, width, depth, and time, not 10 numbers. To answer this criticism, many physicists believe, but cannot yet prove, that the universe at the instant of the Big Bang was in fact fully 10-dimensional. Only after the instant in a creation did 6 of these dimensions curled up into a ball too tiny to observe. In a real sense, this theory is really a theory of creation, when the full power of 10-dimensional spacetime was manifest. Not surprisingly, the mathematics of the 10th dimensional superstring is breathtakingly beautiful as well as brutally complex, and has sent shockwaves through the mathematics community. Entirely new areas of mathematics have been opened up by this theory. Unfortunately, at present no one is smart enough to solve the problem of a quantum black hole. As Edward Witten of the Institute for Advanced Study at Princeton has claimed, string theory is 21st century physics that fell accidentally into the 20th century. However, 21st century mathematics necessary to solve quantum black holes has not yet been discovered. However, since the stakes are so high, this hasn't stopped teams of enterprising physicists from trying to solve superstring theory. Already, over 5,000 papers have been written on the subject. As Nobel laureate Steve Weinberg said, "How can anyone expect that many of the brightest young theorists will not work on it?" Progress has been slow but steady. Last year, a significant breakthrough was announced. Several group of physicists independently announced that string theory can completely solve the problem of a quantum black hole. However, the calculation was so fiendishly difficult it could only be performed in 2, not 10, dimensions. So that's where we stand today. Many physicists now feel that it's only a matter of time before some enterprising physicist completely cracks this ticklish problem. The equations, although difficult, are well defined. So until then, it's still a bit premature to buy tickets at the nearest wormhole to visit the next galaxy or hunt dinosaurs. That's all the information that we have for you today. Don't forget to give us a thumbs up if you've enjoyed today's episode, subscribe if you haven't already, and hit the bell so you never miss out on future episodes. And be sure to also tell us what you think about today's contents. Everyone's support motivates us to continue delivering quality content and to always improve. As always, thanks for watching, and we'll see you next time.